Alright, in the first video of our lesson, in the not first video, but rather l9v4, we actually derived the principle of virtual displacement of the PVD. Alright, so we're gonna utilize this thing now. Alright, so if you haven't watched it, you just watch this video, and then we'll talk about it later. But then, nonetheless, we'll utilize the PVD now in our case. Okay, after knowing our beam system, as we have done earlier. Okay, so let's start. Over here, we know that the stress is equals to Young modulus times strain. So if I were to expand it, I'll have this thing over here. Okay, while the rest are the same. Okay, the virtual displacement, things like that are the same. Okay, so far so good. Alright, and take note that we are still dealing with the linear elastic material because we are subbing in the stress as E strain. This is the linear elastic constitutive equation. Alright, so please be very careful about that. Alright, so let's simply rearrange lah. Okay, so I'll just sub in this one as this one will do. The rest are the same. Okay, the next step I'm gonna do is to sub in my strain and my virtual strain over here. Alright, if you still remember in the previous video, we actually talked about the normal strain, right? Or where if you doesn't ring the bell, you should go and watch this. Alright, we actually talk about it in this manner. Alright, where your strain is your small changes of your radius against the original length of the radius of the curvature. Where the radius is somewhat, don't know why, over here also. Alright, but anyway, we just use the formula. Alright, just use the formula. In the later part, if you happen that you know, you just update with a new video. So therefore, for my strain, I'll sub in as minus y over r. Okay, since you know that strain is equals to minus y over r. Okay, I think you get what I mean. It's from the previous video. Alright, while the virtual strain, I'll just sub in as a minus y over virtual of the radius itself, original virtual radius. Alright, I don't know what the hell the meaning is. Why is it a virtual radius? Dun dun. I think it's because in reality, alright, if you were to bend the beam will have a certain radius, a certain theta angle with a certain somewhat the radius. But it's in terms, if you were to do in terms of certain moderations or stuff, you'll create a radius over here. This is r0. Alright, this line over here is r0, while this one is the radius in relationship to r0. I don't know how, but just take it first. But if you have this is in terms of when you're really bending the stuff. But if you have a virtual bending, meaning it actually doesn't exist at all, it's just having just a beam, but you imagine it that it is bending. So your imaginations, you imagine it with a certain radius. That's all. And therefore, to some extent, you're talking about a virtual radius. Alright. And the next thing that intrigued me is that if I have a virtual radius, why don't I have a virtual virtual displacement over the radius? And these are the stuff that I really don't know what the hell are they doing. Alright, but it's I don't know. Yeah, anyway, I suck. So therefore this poses a question. Alright, just to write it in the description below. In the future, if you happen that you pass by, explain this. Alright, so yeah, save time. Let's continue. So this thing is over here, while this thing is being placed over here, or the rest are the same. You can just double check. Right? Maybe I should say it's not the same. We'll just say that the force 2. Alright, now instead of force or U, we just write in terms of force 2 and U2. Why? It's because if you have a beam over here, your force is acting on node 2. This is node 1. So therefore, force 2, force and node 2 to some extent. Alright, and there will be a displacement, a virtual displacement, because it's all displacement. So virtual displacement and node 2 also. Okay, so to speak. Alright. So I'll just say that this is a brief video because a lot of things I don't understand yet. Alright, but I just want to quickly go through the meaning of it. Alright, the gist of things already. And that k is equals to 1 over r. Alright, just sub in as k equals to 1 over r for goodness sake. Alright, so therefore it's shown over here. Your strain is equals to minus y over r. minus y over multiplied by k, where your k is 1 over r, so it's 1 over r, so it's like y minus y over r. So just take note that your k is equals to 1 over r, and we're going to use this understanding and just sub it in. Okay, so minus y over r, we can simply write this as yk. Alright, because 1 over r is equals to k. Alright, so y, so I have no 1 over r, I have k, so minus yk. So minus yk is over here. Okay, while the minus and because there is minus over here, the minus and this minus cancel each other, so therefore I have still everything over here, while the minus is here, this minus is here, doesn't change the sign. So just take note that when I sub in the minus and minus, they cancel out, so they become plus plus. Alright, be kind of careful of this. Alright, so this thing over here is simply this one, as I rewrite, or this thing over here is simply this one. Okay, where your 1 over virtual radius is equals to your k virtual radius. I mean k virtual k, sorry. So yeah, so in such of a case, then it's minus y, as it should be plus y already, because they cancel each other. So y, and then 1 over r virtual is k virtual. Okay, so we are just simply rearranging stuff already. I mean, in terms of this video, we are simply rearranging stuff for you to see. Alright, so dv now we can change to dA times your dx1. Alright, so dx1, what the hell? So I have a banded beam. This is node 1, this is node 2. Alright, there will be a force at node 2, right? And then suddenly this one is in terms of a dx1. Alright, because we are actually dealing with a small volume over here. If you take this volume over here and then you zoom it out, you have a x, you have a y. Alright, then this is somewhat your dx. Alright, this is your little cube over here, your dA, if you were to say. So over here, this is dx. Okay, so you are somewhat integrating along your this side. So you're integrating piece by piece by piece by piece all along, all the stuff over here. So you're integrating all along dx, all along the beam itself, in this direction. So therefore, it's dx1. Okay, and that's the reason behind dx, but I don't know why is it dx1. Ding ding. After looking at the book, I think that we are talking about in terms of the one direction, alright, or the two direction. So the dx is just wow, chim already. Alright, this is x, this is y. Alright, so in terms of a small dx of this thing in the one direction, so therefore you say that it's dx1. Alright, so I don't know, leave you to think about it. At least I created something for a room to discuss. Alright, anyway, let's continue first. Alright, so the purpose of our step over here is to change dv into dA times dx1, while the rest are the same. Okay, next, after knowing this thing, alright, what we're gonna do, I haven't yet. The y over here and this y over here, you sum it up, you have y square. Okay, so there is a few steps of doing stuff. Alright, so in this step, we expand dv in terms of dA and dx1. We also multiply y and y into y square. Okay, and then the rest are the same. Hopefully, yeah, pretty clear. Okay, so now with this, I'll just skip to the next step now. Okay, the next step, we know that ey square. Okay, I'll just rearrange certain stuff. Alright, I have ey, maybe this is y square. Alright, this dA I'll bring over here. Okay, so I have ey squared dA, okay, and then this whole thing volume first. Okay, for the k, I continue to let it be. Maybe I should just use the same back color. And kv, or this dx1, I'll just write here, equals to 0, while this thing over here is the same. Alright, same minus this one. So only thing that I somewhat switch is only this one. I bring y square, I bring it over here. dA, I bring it over here. I do some integration. Alright, and I will not do integration because I know that this term over here, Alright, this term over here is our I. If you still remember, is our I. I is equals to integration y squared dA, your fracture formula. Alright, or in other words, your I is your second moment of area, while it is related to your stress, alright, your bending stress. Alright, so your this thing over here is your second moment of area, and therefore when you see is EI and then KK the same dx1, or the rest the same is this thing over here. I didn't cheat your feeling. Okay, so now I'll just take EI. I'll say EI is equals to D, some arbitrary notation to say that EI is equals to D. Okay, and therefore I have D over here. So this thing over here I just write over it as D. Okay, that's all. Alright, and then is that dk. Alright, we know that k is equals to what? K is equals to 1 over r. Alright, and d is equals to ei. Okay, so if I have dk in this case, this means that I am taking ei multiplied by 1 over r, right? K is equals to 1 over r. So we have ei over r. And if you find this familiar, this is actually your moment. Okay, so if you take this thing and this thing, if you rearrange, you put I upstairs, you have ei over r equals to your moment, ei over r. So your IFS is here, you just bring it up to here, that's all. Okay, hope this is pretty clear. And therefore, since we know that ei over r is equals to our moment, I'll just simply sub it in. Alright, so my dk now is my m. Okay, while the rest are the same. Okay, and therefore this thing over here, alright, I should have bring this downwards. Alright, is our PVD for our beam in bending. Alright, is our principal virtual displacement for the beam in bending. Alright, in terms of all this, so it's a PVD for the beam bending. And as you see again, alright, you just see properly. In fact, the only thing that is changing across all the subbing in is only about the strain. As you can see, we're dealing with the strain only. The rest are just the rule of the moment and the constitutive equation. But however, the differences between all the PVDs, or between like the bar or the beam or whatsoever later on, you'll keep talking about the strain. What strain you sub in will give you whatever different equations you have. So in this case, we have a strain that is minus y over r due to the curvature of the beam, right? This is the r. I just saw a picture, so I just realized that this is r. You can straight away use r. You don't use this photo anymore. This photo is not good. Alright, this photo is not good. But I think you guys know what I mean because you came from the previous video. Alright, so you should get what I mean already. But nonetheless, just note that that you are just given a PVD. The only thing you need to do is to find your strain. Alright, and find what is the stress equation first. Find your stress equation in terms of whatever strain it is. Alright, and then sub in your strain. Alright, your strain is the key thing. Know your strain already. The rest is just subbing and rearranging. You'll get your PVD for your beam or in bending in our case. Alright, so this is the key concept I just want to convey in this beam bending video. Alright, in the next video we'll talk about using how using this PVD we can derive certain stuff. See you there.